Um, our speaker today is David Heath. David led the Oxford Brookes University team, which designed and built a rocket which gained second place in the UKSEDS National Rocketry Competition while he was an undergraduate at Brookes. He's now studying for a DPhil at the University of Oxford and has become president of the Oxford University Rocket Society. So I will now hand over to David for his talk.
Thank you very much. Good afternoon, everyone. Today I'm going to talk about hobby rockets and whether or not they're just an expensive toy or could potentially be a gateway to research. So just to patronize everyone and go right back to the basics, what is a rocket? Well, fundamentally, a rocket is just a pressure chamber with one side open to the surroundings. Because of their simplicity, they're also incredibly powerful, and that has led to some of the most powerful vehicles ever designed. They're also surprisingly old, with one design by AERODYNAMICS being built somewhere between 428 BC and 348 BC. And this was actually just a wooden pigeon which had a hollow interior that was filled with steam, and when the steam was released through an exit at the rear, the pigeon would be allowed to slide along a line through the central plaza, no doubt to the amazement and surprise of everyone involved. Now, on the right, you can see a slightly more familiar shape, which is the Saturn. This was actually the rocket that took people to the moon, although this is an early version, the Block 1. Which is before the integration with the Apollo capsule. Now, the reason that's up there is that the F1 engines which powered the Saturn V are the most powerful single engines ever designed for rockets, and actually have a thrust each of about 6.7 meganewtons, which is just insane to think about. So I was first introduced to rockets from a mechanical standpoint at university. This was through the United Kingdom Students for the Exploration and Development of Space, UKSEDS National Rocketry Championship. And they design for this championship hobby rockets. So why hobby rockets? Well, basically because they're an incredibly cheap, low barrier to entry way in for students to get involved in the real mechanical side of rocket design. So no competition is a competition without objectives. And for this particular one, it's the highest altitude possible, as well as increasing or including some interesting features. That highest altitude possible mark is actually quite heavily weighted in the scoring, so it really gives rise to some very optimized rocket designs. Of course, without limitations, that just boils down to who's got the biggest motor. And so the limitations on this competition are that each rocket has to use, at maximum, a 2-grain or 160 Newton second G-class impulse solid motor. You also have to successfully recover the rocket. There's very little point in just shooting it into the stratosphere and having it land catastrophically. So you have to recover it safely, but not only do you have to recover it, but you have to be able to relaunch it, which means it has to be safety certified by the range safety officer. And this has to be done within 15 minutes. So the rocket really does have to land in one piece. Now, on the right there, you can see myself and Jared Miller, both members of the Oxford Brookes Aerospace team, with additively manufactured rockets. These were launched at the UKSEDS National Rocketry Championship in 2018 and 19. And I believe the rocket I'm holding over there was the first additively manufactured rocket launched in the UK. So I will try to give my journey in terms of 4 different rockets. I will try to focus on the main design goals of each rocket, as well as the lessons learned during each stage. And I will try to really focus in on the main thrust of each design, pun intended. So the JOULE was the first rocket that I ever designed. It was done during my placement year, which is between your 2nd and 3rd years at university. And the basic design goals were it would have a high strength to weight ratio and really try and go to win the UKSEDS NRC. Now, as all good second-year mechanical engineers know, if you want high strength-to-weight ratio, you immediately go to aluminium. Of course, you do away with any of the explosive charges that are common on all hobby rocket motors for parachute deployment. You do away with that because they're relatively inaccurate on the timing, and you release a parachute with a servo. That would really allow you to precisely release a parachute and control where in the flight you do that, and so you can reduce the aerodynamic forces and therefore optimize the mass of the rocket. Of course, in order to do that, you need to design a flight computer, which has to fit within quite a tight dimension constraint. I'll just point out that the internal diameter of this rocket is about 29 millimeters, so they really are quite tight tolerances. To do that, it would rely on an Arduino Nano. From that, I then produced a detailed rocket design, which I took to be manufactured at the Oxford Brookes workshop, which they very kindly did for me, and hopefully I would launch the rocket. So, takeaway lessons. Well, after I turned up to the launch site, very excited to launch my first rocket, and I was going through the safety certification for launch, I was made very abundantly aware that you're not allowed to launch aluminium rockets under normal circumstances. The UK Rocketry Association actually requires minimizing of metal in the construction of the rocket. And the reason for that is, if you think about these essentially as high caliber projectiles, they can sometimes fail with parachute deployment. And when those come down, they're aerodynamically optimized, so they can come down at about 600 kilometers an hour, which can be detrimental to any objects in the vicinity, whether they're able to move out of the way or not. The flight computer was very slightly harder than expected. It actually turned out that while a prototype was relatively easy to create, actually cramming down all of the electronics and soldering into such a tight space was very, very difficult. So yeah, that was much harder than expected. The parachute mechanism, because of that, was completely ineffective. And so we go back to the age-old solution, which, if you have a problem in rockets, solve it with explosives. You need a stage deployment, explosive bolts. The final issue with that rocket was that it was actually quite expensive. The machining cost alone was about £4,500. The rest of the parts came to about 150, so the body of the rocket was a hugely significant part of the cost. Now, essentially, that rocket was a flying stop sign. There were lots of points in there for improvement, and lots of learning moments to take away. So after that relatively disappointing experience, I came back to my house and immediately sat down and started to design the EPHIALTES rocket. Now, you may wonder about the name. Well, first, the JOULE was named so because I hoped it would take off with a lot of energy and vigor. The EPHIALTES was named because it would get around the metal rules of the UK Rocketry Association. It's actually named after the goatherd who got around the Spartan army at the Battle of Thermopylae. So the main goal, of course, was to be able to actually compete this time in the UKSEDS NRC. At the time, I was very interested in additive manufacturing, and I had just bought a Tronxy 3D printer, which is a very cheap 3D printer at about £100. That does have some limitations, though. It has a maximum build height of 150 millimeters. So you'll notice that the rocket on the left is segmented into 150 millimeter segments. The additive manufacturing process has a number of advantages, though. Firstly, it gets around the rule of the UKRA that you have to minimize metal. The rocket also ended up costing £5.5 per rocket fuselage, which is a massive cost reduction from the £4,500. It also had a massive parts reduction from about 30 parts down to 6. Now, these are typically common when we see additive manufacturing applied to subtractive manufacturing or manufactured parts. The other main benefit was that the flexibility of the additive manufacturing process allowed really interesting aerodynamic features. What you can see most easily on this picture on the right there is that there was a flow discontinuity between the rocket nose and the rocket body. I'll talk more about that later, but that did allow the rocket to be quite efficient. Now, the rocket was simulated to go to 1.72 kilometers with an expected altitude of about 1.43 kilometers. The reason for that is this simulation, one, has some errors, but two, also it simulates the rocket going straight up and down, whereas in reality, the rocket would be experiencing crosswinds and so would more likely follow a parabolic trajectory, limiting the altitude. So I also had some problems getting the EPHIALTES to launch. Obviously, you can understand the guy who last year turned up with a solid aluminium rocket has just turned up with a fully 3D printed rocket. So there were some safety concerns, and I actually wasn't allowed to launch until I literally handed my undergrad thesis to the range safety officer to prove that I actually had some idea of how it would behave. But one of the questions that came back from the UK Rocketry Association on this was about the thermal stability, especially under long-term launching of the additive or additively manufactured parts. So for this, or to investigate this area, I designed the ODYSSEUS rocket, so named because it was exploring unknown areas of the rocket world. So I would investigate the additive manufacturing parts, and in order to do that relatively cheaply, I designed a replaceable internal sleeve. Now that did two things. The first was that it allowed different calibers of rockets, or different sizes, from 24 millimeter to 29, which is a standard, to 38 millimeter motors to be tested. It also allowed tensile specimens to be made without destroying the whole rear of the rocket. So what I could do is test the sleeve that wasn't launched, and then test various other sleeves that had been launched under different conditions, and compare that to original material data to see the degradation or the effect on the material through time. Of course, these multiple launches required a fatigue-resistant body, and as we all know, fatigue resistance means weight. Unfortunately, that meant that the initial design of the rocket was aimed at 3 kilometers and Mach 3, but unfortunately that had to be reduced to Mach 1.5 after the fatigue resistance was applied. It also is a slight issue that the rocket was going so fast. Of course, the thermoplastic PLA that's used has a glass transition temperature of about 60 degrees. And when the rocket's traveling at Mach 1.5, the stagnation temperature on the front of the rocket nose cone becomes a significant structural factor. So after that, I moved on to the development of the von KARMEN 451, which was actually the last rocket designed at Oxford Brookes Aerospace. Now, the idea for the von KARMEN 451 was actually suggested by one of the talented first years involved in Oxford Brookes Aerospace, Julio Meyer, and he suggested that we design it based on the Whitcomb area rule. Now, the Whitcomb area rule essentially says that a body of revolution will experience, well, it experiences drag as it goes through the different speed regimes, but as it gets into the transonic region, there's an increase in wave drag. And what the Whitcomb rule really focuses on is that if you've got a cross-sectional area distribution, that, for example, you would get with wings on an aircraft, it says that the equivalent body of revolution which preserves that cross-sectional area distribution will experience the same wave drag or increase in wave drag. So this gives rise to the idea of wasting in aircraft, where you can decrease the cross-sectional area of the fuselage as the wings start to flare out, so you preserve the area distribution. Or in the case of the rockets, placing the fins in a location which would minimize the transition in cross-sectional area and try to preserve the ideal shape. So on the right there, you can see the cross-sectional area distribution, with the red line being the ideal cross-sectional area. The von Karman is shown in blue. You can see that that's not exactly the same, but quite close. And then for comparison, I've given the EPHIALTES cross-sectional area distribution, which, while a very efficient rocket, still suffered from wave drag inefficiencies. And just to highlight this, with a 1-grain motor, the EPHIALTES was predicted to go to about 700 meters in altitude, whereas the von Karman was predicted to go to about 1.1 kilometers. So it really was a very efficient design. Now, you may also be saying, well, Dave, you're allowed 2-grain rocket motors, so why would you design it for a 1-grain? And this sort of goes back to the idea that these are quite small rockets, and we actually had a number of experiences where rockets got lost just because after 1 kilometer, you can't really see a rocket that's about half a meter long. So in terms of the lessons that were learned and carried forwards, the major one really was keep it cheap and cheerful. It's very easy to set off and just design the optimum body and try and use the most expensive materials. But at the end of the day, if you can't do it within the budget, then there's not really much point. Additive manufacturing was very, very helpful with this. Of course, they allowed, the process allowed very cheap rocket bodies to be developed, as well as quite complex body geometries, which was very helpful for aerodynamics. Of course, it had some disadvantages, the main two being strength to weight ratio. In larger rockets, that becomes a significant factor. And it also suffers from early onset of thermal effects, placing an effective speed limit on the rockets. The last point is just try again. If you're not failing, you're not trying hard enough, as Elon Musk says. So never let failure stop you. So now you've seen the rockets, where is this research that I said that you could get into? Well, while I was designing the EPHIALTES rocket, of course, I had to know how the material behaved in order to be able to design the body. The manufacturer quoted a tensile strength of about 100 megapascals. And as you can see, that was not exactly what came out of the printed parts. So in the X and Y direction, I found that the ultimate tensile strength was about 47 megapascals. And in the Z direction, it was significantly less, about 21.8 megapascals. This is something that we see typically in additively manufactured parts, as well as they have orthotropic properties. Now, for our aerospace friends in the audience, the material's 10th percentile was 15.74 and 41.4 megapascals, and this is what you would design the rocket to if you were looking for maximum safety. Of course, I was looking for maximum performance, and if the rocket fails due to the safety precautions at the launch site, it's not catastrophic. So I designed everything for the Z direction, just so I didn't have to optimize for orthotropic properties. I also had to do some structural validation, which you can see the rocket placed in the the compression trig in the left-hand photo. And if you notice at the bottom there, the fins were actually, the whole rocket was printed as it would be, and the fins were graciously removed to enable it to fit on the jig. Now, the buckling constraints there are very interesting. The rocket actually falls into a slenderness ratio where it's in the complex buckling region. So you can't exactly predict it using the Euler buckling equations or simplify it down to just crushing. And so there's quite a few equations in that region that vary depending on their, or vary in their accuracy depending on the material behavior. And so I tested them all, or predicted the failure, and found that the Rankine-Gordon was actually the most accurate. Now, the constraint conditions between the testing and what you can see on the right, which is during flight, were slightly different. During the testing, the width of the rocket body actually stops the body deviating. So that gives a buckling constraint, or alpha, of 4. And on the right, you can see that essentially the only thing that's stopping the rocket from buckling is the fins, or moving is the fins. And so the buckling constraint was 0.25. Aerodynamics are very important for rockets. And so the first thing I did was wrote a MATLAB simulation to allow me to really focus in on which regions would need to be optimized for. The first thing I did was look at the time analysis, which showed that about 90% to 100% of the rocket's time was spent in the subsonic region, and from 46% to 75% was below Mach 0.3, so in the incompressible region. So if we just looked at that, we'd think, okay, well, we're clearly optimizing for incompressible flows. But where the analysis gets really interesting is with looking at the drag impulse, where up to 23% was in the transonic drag, and between 79 and 89% of the drag was generated in the compressible region. Now, this is because drag is heavily weighted to the velocity of the rocket being a squared factor. And so that gives rise to a targeted optimization of compressible flows. And in order to do this, Oxford Brookes very kindly let me use the wind tunnel, which is shown there. Unfortunately, the wind tunnel doesn't go up to 300 meters per second. It was capped at around 25 to 30 meters per second. So what I did was I did a simulation at 25 meters per second, and then I tested the rocket at 25 meters per second. And I used that to calculate the actual drag coefficients at 300 meters per second from the simulated drag coefficients. Now, block 1 was actually what I designed after I came back from that first competition. And it wasn't, it used, for example, a 10-degree angle nose cone. And the reason I did that was because we et al. 2005 used that when they were investigating aerospike nozzles, primarily because that nose cone provides very predictable flow conditions downstream of the nose cone. Unfortunately, that doesn't translate to very high efficiency. So the first thing I did in block 2 was to change to an ogive nozzle, not nozzle, nose cone, which is essentially a segment of a circle. And what you can see is that at 300 meters per second, the rocket had a drag coefficient of about 0.44 and a real drag area of 719 square millimeters. That 790 square millimeters is actually very important because that's actually what's causing the drag on the rocket body. And so we need to watch that to see whether our drag reducing steps are actually positively affecting the drag. And what you can see is from 2 to 3, that wasn't the case. But what I did do was I changed from a flat fin to an aerofoil, symmetrical in both planes. That did actually increase the drag coefficient, or decrease the drag coefficient, but it increased the overall area because the aerofoil was slightly wider than the flat fin, which meant it actually had a negative impact on the drag. But you can see from 3 to 4, there was a massive drop-off in drag. And this was actually really interesting because rockets are very thin objects which essentially travel in a straight line, which means that the dominant drag effect is skin friction drag. And what I did here was I increased the nose cone slightly so that there was an offset between the nose cone and the body, and that tripped the flow to turbulent flow, which has a lower skin friction drag than laminar flow. And that's what had that massive impact on drag. It's also been shown that that same effect protects the rocket from thermal effects at higher velocities, so it's useful across a wide velocity range. From block 4 to block 5, you can see there's a very slight drag reduction, and all that is that there was a slight hump placed at the back of the rocket, and what that does is it tries to catch that turbulent flow and reattach it to the rocket to try and reduce the bluff body effect at the back of the rocket. This is also quite important in terms of how the nozzle functions. Block 6 and 7 weren't, they were internal changes, so there was no aerodynamic benefit from those two. So moving on to the nozzle, going back to how a rocket operates, if a rocket is just a pressure chamber with one side open to the surroundings, what the nozzle is a constriction which accelerates the flow up to Mach 1, and then takes advantage of the odd behavior of supersonic gas to accelerate as it's expanded through the Prandtl-Meyer expansion mechanism. Now, what that also allows you to do is, for example, utilize that expansion fan to turn the flow so that the velocity vectors are all aligned with the direction of motion of the rocket, which is why bell nozzles are so efficient, and also why conical nozzles are slightly less efficient because they don't completely align the thrust vectors. However, both conical and bell nozzles suffer from changing expansion ratios, or a need to change expansion ratios as a rocket increases in altitude. Of course, the pressure outside decreases, so the ideal expansion pressure decreases as well. Unfortunately, due to effects that would basically cause flow separation and then destroy the rocket, the expansion ratio has to be set at the maximum pressure experienced during flight, which is usually the sea level pressure, which means that both bell and conical nozzles suffer from a loss in expansion efficiency over the flight regime. Now, a very interesting nozzle is the aerospike nozzle. And that actually allows a continuously variable expansion ratio up until the maximum expansion ratio. And how it does this is, if you see over here is the cowl, or on the model, the cowl there, that is the origin of the Prandtl-Meyer expansion fan. And that fan actually reflects from a solid surface as an expansion fan, but it reflects from a fluid surface as a compression shockwave. And how the aerospike nozzle really works is it allows the gas to expand down the surface while allowing the flow to form this shear layer on top of the gas. And that allows the expansion fan to generate a compression shockwave, keeping the gas at the ideal expansion for the external pressure at all times. Now, a very obvious question is, well, hobby rockets are quite small and they don't go very high, so why would you need a variable expansion ratio? And here's where you get into a very interesting effect, which we mentioned, that bluff body effect earlier, that actually leads to a low pressure region behind the rocket, which is about 75% of the atmospheric pressure. And that gives you a little bit of room for increased expansion efficiency and so increased thrust. And so what you can see here is the blue line here is the atmospheric expansion design, whereas the red line is the flow conditions, or 75 kilopascals design. And what that meant functionally for the EPHIALTES rocket was that the original nozzle produced 83 newtons of thrust, whereas the aerospike nozzle there produced 96.3 newtons of thrust, which is a net increase of about 16%, which has a real meaningful impact on the altitude. Another piece of software I wrote was a simulation to calculate the rocket's flight. And you can see here that that simulation was very, very useful. It showed the maximum altitude as well as the velocity, the rocket's acceleration, the drag, and also the parachute impulse, which was particularly useful in designing the bolts and attachment points for the parachute in the rocket. On the right here, you can see the rocket on the launch pad before flight. And on the far right, you can see there's a shot of the rocket in flight. Unfortunately, the image quality is not great. And the reason for this is both the rocket takes off with about 30 Gs, so it's really moving quite fast. And secondly, due to the safety constraints of the launch site, you have to be quite far away from the rocket when it launches, which means that that's actually an incredibly zoomed in shot. But what I do like is that you can see the exhaust trail there from the rocket. And as I mentioned earlier, the rocket was predicted to go to 7.9 meters, but due to crosswinds, eventually only went to about 666 meters, which is an incredibly unfortunate number. So how has that all led to my current work, which is with the Oxford University Rocketry Society? Well, I've produced a small concept design here, which I will stress is probably not what the rocket will look like in the end. There are about 30 people working on it. And the regions that I'm actually working on are the injection plate and the aeroswipe nozzle. But in terms of what I would ideally like to see in the rocket, the aeroswipe nozzle for increased efficiency, specifically on the hybrid motor there. There's a flow discontinuity to increase the aerodynamic efficiency and also mitigate some thermal effects. It would be made out of carbon composite because at this point the rocket is just too large for additive manufacturing to really play a massive role. And what I will just stress on that point is that the diameter of this motor is about 150 millimeters. So it's quite a large step up from the hobby rockets we're talking about. And the final goal is to get to about 100 kilometers within the next 5 years. So in summary, a lot of this is learning through failure. Just keep trying and take one opportunity to optimize a single aspect per rocket. Basically, your first rocket will never be the best, so try and optimize an aspect and build on that for the next one and the next one, and keep going until eventually the dream will become the reality. Any questions?
Right, thank you very much, David. I have one question has already come in. So how long can the spike be before it melts?
That's actually a very difficult question to answer. But you're absolutely right. Aerospikes do suffer from thermal effects, specifically around the tip. And what I showed there was a truncated spike, because you'll find that just due to the thermal mass, most of the detrimental heating actually takes place beyond 75% of the launch. The length. And so one of the things that you can do to reduce that is to truncate to about 75%, and you only lose a very small amount of the efficiency of the aerospike if you do that.
Okay, thank you very much. Right, what is the propellant?
So for hobby rockets, the propellant is ammonium perchlorate, which you can buy the motors through just off-the-shelf retailers. But for the actual hybrid rocket, we're using HTBB rubber and a nitrous oxide oxidizer. So yeah, those are two propellants we're mostly working with.
Okay, well, while we're waiting for any further, the hybrid rocket that you're working now, is that designed for a competition, or is this purely a piece of your own challenge, as it were?
Yeah, so it's just I'll put it back up on the screen now, actually. It's just for our own challenge. And essentially, there's this informal challenge around the world of different student groups. And there was an American group that was the first student group to launch a rocket above 100 kilometers, but they did that on a solid rocket motor. There's also a very famous rocket team designing a solid fuel motor to go up to 100 kilometers, which is Delft. So we thought we'd take a slightly different view on that. Hybrid rockets are very, very interesting. They're also starting to move more in the literature as a throttleable but still easily and cheap design of rocket, because of course you can't throttle solid fuel. And so that's really the goal, is to try and be the first student team to launch above 100 kilometers on a hybrid motor. If that answers the question.
Okay, the two more coming. Have you considered a two-stage rocket for fun, if nothing else?
We have. I believe the team last year looked at a two-stage rocket. Unfortunately, two stages are quite complex. So I think that's something we'll work on in the future, but they are complex and tend to lead to failure more than success some of the time. So it is something we've looked at, yes, though.
Okay. And coming back to the aerospikes, do you see aerospikes as the answer for single stage to orbit craft?
Yeah, so the short answer is, if you're going to do a single stage to orbit, an aerospike is the best nozzle that you can use, depending on various other things. So, for example, one of the reasons that an aerospike is really good in both a solid fuel and a liquid fuel, a hybrid fuel, is because the characteristic length of the rocket is not limited by the annular chamber of the aerospike, whereas in liquid fuels you tend to see a limitation of the characteristic length, which means that the actual combustion of the rocket is slightly less efficient. So I would suggest that, like I think it was the X-34 from NASA, that would be a really good design for single stage to orbit. And you would, of course, need pressure compensating designs for maximum efficiency. So I do think it's a good area to look into, although there are constraints. But
okay, thank you. Aerospikes are not really scalable, or are they? Larger versions have all suffered from thermal issues. And aerospace, yeah.
Yeah, no, that's absolutely correct. So aerospikes are scalable in the sense that you can make bigger ones, but you're absolutely right in that they do suffer from thermal effects, and that's an area of active research and literature. What a lot of them have tried to do is basically just focus on active cooling to keep the rocket thermal effects down. But basically there was a design put forward a couple of years ago where there would be a JOULE expansion design, which essentially would rely on the heat from the combustion chamber for the fuel and the heat from the aerospike nozzle itself to expand the oxidizer. So there are methods which you can sort of claw back some of that effectiveness despite the thermal effects.
Okay, thank you. I had a question. How do you trigger the parachute to get it at the right time, that it doesn't deploy too early and does actually deploy in time, so the thing doesn't come crashing down?
Yeah, so that's actually that's why with the first design I wanted to go for a servo deployed one, because the explosive charge on the top of the commercially available rockets have an error of, I think it's about a second, something maybe half a second. But at the end of the day, they are much, much more reliable. So all you do is you strengthen the attachment points to be able to survive under all of the conditions within that time frame. And then you just really, really hope that it's more accurate than the other.
Sorry, I think we lost you there, David. If we...
Oh, sorry.
It just clipped the end, possibly. Not to worry.
Right.
Okay, are there any... don't think there seem to be any further questions coming through. I'm sure if anyone does think of a question they would like to ask, then if you email me, I will pass it on to David, the question on to David, and I'm sure he will be willing to answer outside of this event. So at that point, can I thank you very much, David? It's been really interesting. I've learned something, and it's not an area that I knew anything about. Clearly, there are one or two in the audience who know a lot more, and we're asking some very detailed questions. So thank you for the way in which you dealt with those. So thanks to David. Right, and I've got thank yous coming up from the audience as well. I will stop the recording.